Hello everyone, and today we're going to be talking about optimization. So I guess the fundamental question we ask with every one of these videos, so what is optimization and why do we care? Optimization is a really general framework to look at a lot of problems that we try to solve in robotics. So a collection of some of those problems can look like this. Trying to find what is the optimal or best action given my situation. So let's say I'm playing soccer, I'm trying to figure out when should I shoot? That's a question we can ask. Then we also have what is the optimal or best path? Let's say I'm a robot trying to go through an obstacle course. What is the best way to get from point A to point B? We can use optimization to do that. We can also use optimization to do what is the best state? I've said optimal or best a lot. And I've kind of been vague about what that means because I haven't really defined it. So what does it actually mean? So usually we have this thing called an objective function. And an objective function is the thing that defines how good or bad something is. So we have this f of x, which is going to represent our objective function. It's a mapping from our state vector, or some vector that represents our state, to r. So this is just saying some real number that represents how good or bad we are. Now there's kind of two ways of looking at this. So there's the optimist perspective for happy people like you. And they are, we get rewards for doing good things. Yay! There's also the really pessimistic viewpoint, and this is what we often use in controls. And you get a penalty for doing bad things. So that's bad, boo, instead of yay, that's good. And obviously I'm a grad student, so we're going to use the pessimistic perspective that we use in controls. And we're going to be looking for things that minimize our cost rather than maximize our reward. So the next thing we can talk about is constraints. So now that we've figured out what optimal is and what the best thing could be, often we have restrictions on what we can do. And these are what we call constraints. You can either satisfy a constraint, which is where you meet it, or you can violate a constraint, where you break it. So what you want to do is find what is the optimal action and what is the best thing to do without violating any constraints. So the way you typically write constraints are things like this. You have some function g, and you have a collection of these functions, which is why I have the subscript I here. So the first constraint function I have is the first position of my x vector must be greater than 0. I can also have things like g2 is less than d, where g2 just returns the distance to an obstacle. So I want a distance to my obstacle to be less than d. I can have g3, which is equal to 0, so essentially say that my dynamics of the vehicle must be satisfied, so my vehicle can only move according to my dynamics and can't do arbitrary weird things in between. I also have constraints that are based off sets, so we can say that such that our output x is in some set omega, where omega has some properties. So these are the different ways we'll write constraints, and if we take an objective function and we combine it with some constraints, we get this thing called a program. Now, I won't go into the history of why it's called a program, but this is what we usually frame an optimization problem as. So you'll see things like, oh, we have a linear program, or we have a quadratic program. And these are just optimization problems of specific families. So this is how you'll write a program or an optimization problem. So you have what you're trying to do, whether you're trying to minimize or maximize your objective function, what the actual objective function is, and then subject to, so what constraints must I follow, and then you'll list out your constraints. So we can frame all sorts of problems like this, as we talked about earlier. So what is my best action? What is the shortest path? So the important thing to remember is that maximization and minimization are very related, essentially the same thing. So I'm going to show this notation here. So we have an argmax. So we talked about earlier when we had minimize f of x. That means find the minimum value. So what is the actual output of f at the minimum, rather than what is the input vector x at the minimum. So argmax is essentially saying what vector x is actually truly a minimum. So the important thing to remember is that the argmax f of x is equal to the argmin of the negative objective function. So that's essentially just saying that maximizing and minimizing are related, and you'll get out the same value as long as you're using the correct transformation on the objective function. So the way to look at that is, let's say this is our f of x, and this is our negative f of x. So if I'm trying to maximize this, the maximum value is here, and I'm trying to minimize negative f, the value is here. And see, these are the exact same value, therefore this equality is true. So now that we've been talking about optimal for a while, let's define what optimal means mathematically. So we have, let's say we have an optimal solution x star. A lot of times you'll take the variable that represents your input vector and add a star to it, and that'll represent the optimal value. So let's say we're trying to do some argmin over some set capital X. So the thing we're doing in the argmin across is the entire set capital X, where little x is a member of that set. So we're doing the argmin, so we're going to get out some input vector x, which represents what's the input vector that gives us the lowest value for f. And essentially what that means is the value at f for x star must be less than or equal to any other value of f for any other vector in x. So if x star was not optimal, this inequality would not be true. There could be another thing that is a lower value, and if anything is a lower value, that is actually the optimal value. The optimal value must always be less than or equal to. Now there can be multiple optimal values that have the same output f given different input x vectors x, but we're going to ignore that for right now. Now we've talked about the definition of optimal, we can talk about different types of critical points. So we can talk about local minima or local maxima. So I'm going to define some x here in our set x such that the distance between some x and some x star is less than some value d. So this distance essentially means that, let's say I have some number line, I have some x star on this number line, and I'm looking at the values that are around it, so in the neighborhood like this, so that their distance is less than d. So if I have a weak or local optima, what you see is something that looks like this, and there could be multiple values along this top here that all have the same objective function value, so their value of f is the same. So the one's not really better than the other, they're all about the same. You can also have strong, where you only have a single value at the top that is the same. And you can also have this in the local and the global context. So the local context just means we have a limited neighborhood of those around us, and the global context means that our neighborhood encompasses all values. So this is true for any value instead of just the ones near us. So let's look at some different types of minima. This is our global minima, and we have things like this would be a local minima. Local. And this would also be a local minima. So oftentimes when we're doing optimization, you have a lot of different things that look like this. You'll have lots of local optima, and you can even have a couple global optima. But the thing to remember is what you're trying to do is find this global here. Because you want to find the lowest value for all possible input vectors, but oftentimes you'll have to suffice for something like this, which is what is the best I can do in my neighborhood. There are different types of functions, and the first type of function that's really important is a thing called convex. If an objective function is convex, that is true if and only this inequality is true. And essentially all that is saying is that every local optima is also a global optima. And what you can do is for anything on a convex function, you can take 2 points and draw a line across it, and you won't intersect with the convex function. So if I have something, I can draw a point here and a point here. So a lot of things that you've seen like parabolas are convex. There's a lot of different convex functions, and convex functions are what you really want to be solving when you're doing optimization. So the properties of convex function is every local minima is a global minimum. So this is really nice. So if we have some algorithm that could get us to a local minima, and we know that our objective function is convex, we can say that that is also a global minima. We have found the best possible value. So there's things called a strictly convex function. That means there is at most one global minimum. So that means if we find some local minimum, it has to be a global minimum because it's a convex function. And since it's strictly convex, there's only one of those, so we found the best value possible. Convex functions are much easier to solve than non-convex functions. So anytime you're doing optimization, you really want to try to find some way to make it a convex problem rather than try to solve some really unwieldy non-convex problem. So convexity is closed under a couple of operations. And essentially what that means is, given I have a collection of convex functions f1 through fn, if I combine them in specific ways, the output will also be convex. If I had a lot of different objective functions, like what is done in RoboCup, and if all of them are convex, that means that if I do a weighted sum of them, so I combine them together, the output of that is also convex. So if you take these little parts and combine to a larger whole, you can find a nice convex function that will represent what you're trying to do. The max of a collection of convex functions is also a convex function, and a linear mapping of a convex function is also a convex function. So we talked a little bit about concave functions, but the thing to remember is that we can find local minimum, but those are often not global minimum. The two do not have to be related at all. I can have a bunch of those little bumps and find all of them, but I won't necessarily find the global. These are really hard to solve. This is kind of an open problem still, and often how we tend to solve these functions is we use algorithms that are designed for convex functions, and they usually do okay, but not super great. So this is kind of what a concave function would look like. As you can see here, we have lots of different local minima. So in summary, optimization is a really important part of robotics because it makes up a large part of our tool set. We use optimization problems to train things like machine learning models. We can use optimization to do things like localization. We can use it to find the shortest path, and we can also use it to find the best action. Now this is a wide range of different objectives, which is one of the reasons my advisor kind of looks at the whole world as one giant optimization problem.